Hi, this is Miss Logan. Today I'll be covering forces, which will include free body diagrams, net force, and how we're going to use F equals ma. This slide is just a reminder for Newton's 3 laws. The first law, remember, is our law of inertia. Things will stay in place until they are moved by an outside force. The second law we will be using often, which is F equals ma. The last one, for every action there's an equal opposite reaction. We'll use this in this unit, but we'll use this even more when we're talking about momentum and energy. All right, so we're going to briefly review contact and non-contact forces. Contact forces have to be in contact with an object to cause acceleration. Non-contact forces are creating a field and can cause acceleration even when not in contact. So let's remind ourselves of these different contact forces. First one is applied force, so maybe I'm pushing on something or pulling. Friction, which we will talk about in our next flipped lesson, is a force that's actually going to slow things down. Our normal force is our support force. We are often going to see this when an object is sitting on something else. We have gravity, and then when we have normal. Then we have tension. So this is when we have a rope or a string. Spring force, we need to have some type of spring, and there are a couple different laws associated with this. Centripetal force is with circular motion, which we will not be covering in this unit. Non-contact forces, the big one is gravity. Gravity, as you may remember, is also weight. So weight equals mass times gravity. We will be using this equation often when we are solving problems. The electrostatic force is force from electricity. We will be using this later in the year. All right, so when are we going to use these contact and non-contact forces? We'll be using these in free body diagrams. So as you may remember, force is a vector, so it has a magnitude and a direction. A free body diagram is a diagram of force vectors acting on an object, nothing else. Your pictures should be simple and just show the forces that are acting upon an object. You do not need to show anything else. So these questions are from the pretest that you took a few days ago. An egg is free falling from a nest in a tree. Neglect air resistance. Remember, the word neglect means do not use. You will see this word very often in these problems. So let's think, what different forces are acting upon this egg? First, we have gravity. We won't have normal, it's not supported, and we are neglecting air resistance. So our answer is C. A softball is tossed upwards in the air. Neglect air resistance. The ball has already left the hand. So let's think about different forces. First, we have gravity. Remember, gravity is going to be in about 99% of our problems. It's always pulling down. We also have applied force. Why? Because of the hand. So our answer is C. A softball is tossed from the pitcher's mound to home plate. Neglect air resistance. The ball has already left the hand. So let's think. We have gravity, which we are always going to have. And then we also have applied force. Let's think, what direction is this going? It's going to the right. So we'll have A. We have our force of gravity here, and then our applied force here. So now we're going to get into how we will be using Newton's second law in these problems. As you may remember, net force is the total force on an object. This is often denoted with this symbol and F. That is sigma, that is the total of something. So we first have not in equilibrium. If something is not in equilibrium, it is moving. If something is in equilibrium, it is not moving. So when we are in equilibrium, we'll use our force, our total force equals mass times acceleration. If we are in equilibrium, we know our total force equals 0. So I'm going to go through some examples and show how we would start to set up these problems in a conceptual way and then using numbers. So the steps we're going to take is first to draw a free body diagram and include all forces on the object. If they give you numbers, you also need to include these as well. Then you need to write down the force equation in the x and the y directions. Now you need to determine whether your object is in equilibrium or not. Then you can solve. Let's do some problems so we can see this in action. Scenario 1, an apple is falling from a tree. So, the only force we have is force of gravity. So the equation we would use, F equals ma. Why did I decide to use this? This is not in equilibrium. It's falling. So our force equals to our mass, but I can replace this acceleration with gravity. Why? Gravity is 9.8 meters per second squared. It's an acceleration. Second, an apple is sitting on a desk. So I'm going to draw my free body diagram. I have gravity down, normal up. So this is an effect of Newton's third law, equal and opposite reaction. So this thing is in equilibrium, so we know my total forces equal 0. So I have Fn plus Fg equals 0. That's my net force on this object. Now we have an apple hanging from a rope. So I still have gravity. Now I have force of tension up. So think to yourself, is this thing in equilibrium? Yes, it is in equilibrium. So we need to use our equation, total force equals 0. Now we have force of gravity plus force of tension equal to 0. I push an apple resting on a table. So I have an applied force, I have gravity, and I have force normal. In my x direction, am I in equilibrium? No, I am not. So I will use force equals ma. So my force applied equals m times a. In the y direction, I'm in equilibrium. So I have my total force equals 0, which will be my force of gravity plus my force normal equals 0. I push an apple at an angle of 45 degrees. So I'm going up, force applied, with 45 degrees. In this example, I'm going to not include force normal and force gravity just to make it a little bit easier. So what do I need to do to figure this out? Because we know I'm not in equilibrium. So let's write my equations. How am I going to get this force in my x and my y? Now I need to use sine and cosine. So in my x direction, remember I'll be using cosine, I'll have F applied cosine 45 degrees equals ma. In my y, I'll have FA sine 45 degrees equals ma. All right, so we looked at different pictures. We weren't using numbers. Let's actually use numbers this time. So we have two forces that are acting on a 55 kilogram block. That's my mass. The magnitudes of the forces are 79 newtons and then negative 41 newtons. Remember, this negative is telling me this is going the opposite direction. What is the horizontal acceleration of the block? So think a moment to yourself. Is this thing moving or not? It is. It's asking for acceleration. So we have F equals ma. First thing I need to do is figure out my net force on this object. So I have 79 minus 41. That'll give me 38 newtons. Let's plug these things in. So I have 38 newtons equals 55 times my acceleration. So now let's solve for acceleration. I'm going to divide by 55 on each side. And for my acceleration, I will get 0.69 meters per second squared. Next problem. In a grocery store, you push a 14.5 kilogram cart with a force of 12 newtons. So let's just assume it's going to the right with 12 newtons. So how far does it move in 3 seconds? So this is a problem where I will be using other information and other equations from different units. So let's first use F equals ma. It's moving. F equals ma. I have 12 newtons equals 14.5 acceleration. Let's solve for acceleration. I'm going to get 0.83 meters per second squared. However, that's not what is asked in the problem. It's asking how far does this move? So now I'm going to turn to my kinematics equations. The first kinematic equation, d is equal to 1/2 at squared plus v0t. Let's assume this thing started from 0. Let's plug in my numbers. I have d equals 1/2 a, which I solved for, times time squared. So for my answer, I'm going to get a distance of 3.72 meters. So a lot of these problems will have you solve using Newton's second law and then use your kinematics equations. All right, so please pause this video and work on these follow-up questions. Remember, do these to the best of your ability. It's for me to see what you know and what we need to review in class.